Use the function to answer the following. I have f of x equal to 4 multiplied by 0.5 raised to the x power. Now, the first thing that I want to point out is that inside of the parentheses, the part that's getting exponentiated, this quantity is less than 1. It's bigger than 0, but it's less than 1. So if I keep on multiplying this by itself, this is just going to get smaller, smaller, and smaller. So I can immediately deduce that this is going to be decay. And for decay, the general formula would be f of x equal to the initial value a multiplied by the quantity 1 minus r raised to the t power. Here I have x, but it would be the same thing if I had f of t. Now, to find the rate, I want to point out that the quantity that's inside of the parentheses is represented by 1 minus r. So I'm going to let 0.5 equal to 1 minus r, and then I'm going to solve for r. That's going to give me the rate. On both sides, I can begin by adding r. And on the left-hand side, I'm going to get r plus 0.5. I cannot combine these two quantities since they're not like terms, so the only thing I can do is to express them side by side with that addition symbol. But on the right-hand side, once the r's cancel out, I'm left with 1. To completely isolate r, I can subtract both sides by 0.5, and I get that r is equal to 1 minus 0.5, which is just 0.5. So my rate is 0.5. What is the initial value? The initial value is going to be the quantity that's in front of the exponential part. So here I have my base of 0.5, I have my exponent of x. So the initial value is going to be the quantity that's in front. That's going to be this 4. Finally, I'm going to evaluate f of 3. Everywhere I see an x, I'm going to replace it by a 3, and then I'm going to simplify. So f of 3 is equal to 4, quantity 0.5 raised to the third power. Now 0.5 to the third power, that's going to be 0.125. And then 4 times 0.125 is just going to give me 0.5. So f of 3 would equal 0.5. Let's look at another problem that's very similar. This time we have the function f of x equal to 5 multiplied with quantity 1.2 to the x power. Does this equation represent growth or decay? Well, I know that my leading coefficient is positive, and on top of that, my base, it's bigger than 1. So if I keep on multiplying 1.2 by itself over and over and over again, the more that I do it, the more that this is going to grow. So I can immediately deduce that this function represents growth. So this is going to be exponential growth. For the rate, well, if I look at the generic outline for growth, we have the function is equal to the initial value a multiplied with the quantity 1 plus r raised to the t power. And here there is a typo. This x should really be a t since we're expressing the function in terms of t. But to get the rate, I'm going to let 1.2 equal to 1 plus r. And again, I'm using 1 plus r because this is growth. If it were decay, I would have used 1 minus r. Now here I can easily isolate r just by subtracting 1 from both sides. On the right hand side, I'm left with r. On the left, 1.2 minus 1 is just going to give me 0.2. So my rate is 0.2. As for my initial value, well, my initial value is going to be the number or the quantity that's in front of the exponential part. So in this case, that's going to be this 5. And for the final part, I'm going to evaluate f of 5. So everywhere I see an x, I'm going to replace it with a 5. And by doing this, I get f of 5 equal to 5 multiplied with quantity 1.2 raised to the 5th power. Now 1.2 raised to the 5th power, I'm going to approximate this to 2.49. So now I have an approximation, and then 5 multiplied with 2.49 is going to be approximately 12.45, and that would be f of 5.